Hello, this is Claire back, and we're going to talk about measuring some side lengths and practicing our sine, cosine and tangent ratios. So I've drawn here a triangle, and I'll get you to draw the triangle too. The base I've made 12 centimetres and I've just measured 4 centimetres and 8 centimetres here. And I've marked that off. The small triangle I'm going to call triangle A. And I've used my protractor to construct a 30-degree angle here. It's not essential, but it's probably helpful if we all use the same triangle. So I'm measuring from here and I've gone up 10, 20, 30. Put a dot. And from the line, from the corner, I've constructed a line up till I'm just above the 12 centimetre mark. And I have then drawn the other lines to define the triangles. Now these triangles here are all similar because they all share this angle theta here. They share theta. They all have a 90-degree angle. And if we calculate 180 minus 90 minus 30, this must be 60 degrees up here. So they all have the same angles. So they are similar by angle, angle, angle. So that's actually a proof of similarity. So similar because the three angles are equal, and they are similar because they are of different scale ratios of each other, but they are in proportion. So this small triangle we're going to call size A. So you can stop the video and draw that triangle. And we're going to construct a table too. Now this is a simple table. I could have made it a bit more complicated, but let's keep it simple. So the triangles that I'm talking about are A, B and C, small, medium and large. And we're going to calculate the sine ratio, which is the opposite over the hypotenuse, and put that in here. The cosine ratio, which is the adjacent length divided by the hypotenuse, and the tangent ratio, which is the opposite over the adjacent. And that word sine, cosine and tangent are simply describing the ratio of two particular sides. So that's what that's doing. Okay, so I've just written SOHCAHTOA here, and you could write it the other method also, which I kind of like actually a bit more because it helps you remember that they're divided. So either method is fine. Now we're going to put in the fraction and then convert it to a decimal. So in the first angle, and remember to stop the video if I'm going a bit too fast for you. So in the first one, we're going to look at the opposite over the hypotenuse. So here's theta. This is the opposite side here. So we'll measure that. And just to the nearest millimetre, it appears to be 22 millimetres. So it's going to be 22 divided by, and we'll measure the hypotenuse of that first triangle, which looks to be 45. Well, there's going to be a little bit of an error here, human error. So getting our calculator and clear that. So there's our calculator, and we're going to go 22 divided by 45 and enter, and round that to, let's round it to 1 decimal place accuracy. So it says 0.4 and 8 is above 5, and it's going to round up to 0.5. Okay, so I've just put 0.5. It's very close because 22 over 44 would have been perfect. We'll round that to 1 decimal place accuracy. So let's look at what the sine of the second, in the second triangle, triangle B. So this is the opposite side here. So measure that, and it's 45. So 45 millimeters, and the hypotenuse of the second triangle is 90. So 45 over 90 is a half, is it not? So we could say that it's also 0.5. Now let's look at the opposite side length in the largest triangle, triangle C. Let's measure up there. It's 70 millimeters. Let's double check. Yes. And the hypotenuse is 140. So again, you can see that twice 70 is 140. So that would be a half, or 0.5. So as you can see, the sine of each of those angles is exactly a half. So as you can see, a small triangle, if it has that same angle, the sine of that angle seems to be the same no matter how big I draw the triangle. Let's look at the cosine now. The cosine is the adjacent length. It's the adjacent length divided by the hypotenuse. So let's look at the adjacent length. It's 4, as we would have expected, 40 millimeters. And the hypotenuse is 45, which we measured before. So 40 divided by 45. Clear our calculator. 40 divided by 45 equals, so it's 0.88 or 0.9. So we'll write that as 0.9. Let's look at the next one, the next triangle, which is triangle B. We've got 80 millimeters, and the hypotenuse of that was 90. So 8 over 80, or 8/9, should be 0.8 recurring, which would be 0.9, but let's just double check that. So on our calculator, we go 80 divided by 90 equals 0.8 recurring, which is exactly what I got before, which rounds to 0.9. In our last triangle, again, we're going the adjacent, which is 120 over 140 was the hypotenuse length. So clear. 120 divided by 140 equals 0.857, and if you round that to one decimal place, it's 0.9. So the cosine of the angle, the cosine of 30 degrees here, is going to be exactly the same no matter what size I draw the angle, I draw the triangle. So as long as that angle is the same, you're going to have a similar triangle, and you'll have exactly the same measurement of the cosine ratio and the sine ratio. What about the tan ratio? So let's look at the tan ratio. It's the opposite over the adjacent, and we should have these measurements already. So the opposite here, we had 22. So that's 22. Let's just check it. 22 is good. And the adjacent we had is 40. So 22 over 40 on our calculator. Let's clear that. 22 divided by 40 is 0.55. Rounded to one decimal place is 0.6. let's look at the next one. In triangle B, opposite, it's going to be 45 over adjacent is 80. So clear. 45 divided by 80, 45 divided by 80 equals, again, rounding to one decimal place, the 6 rounds that up to 0.6. So it's the same. And let's look at the last one. The opposite over adjacent. So we measured that as 70. And that's 120. So clear. 70 divided by 120 is, again, round that 8, we'll round the 5 up one place to 0.6. So what have we learned here? We've used a 30-degree angle. So these measurements that we've taken are really unique to using a 30-degree angle. So in a 30-degree angle, the sine of 30 degrees, the sine of 30 degrees here is clearly going to be always 0.5, okay? And here it's exactly 0.5, and here the cosine, so the cosine of the 30-degree angle here is approximately equal to 0.9. I think it's actually 0.866 in reality. And let's look at the tan of the angle. The tan of 30 degrees, no matter what size the right angle triangle, we have it here as approximately equal to 0.6. Now on your calculator, we can find out exactly what those are. So let's just clear that. Let's have a look at your calculator. You can see you have sine, cosine, and tangent. Okay. Up on your display, you might be able to see if it says a D for degrees up here, or a DEG, which means degrees. You do need to make sure that your calculator is in degrees. So you can do that with the mode. And if we look in the comp mode, math mode, it should give you degrees. It should default to degrees. So let's look at what the sine of 30 degrees is. Close my brackets and equal 0.5. Tick. Okay, clear? Let's look at the cosine of 30 degrees, close, and equals, it's 0.866. So it's an approximate, it's not exact. So it's actually 0.866, but it's still approximate. And we got 0.9. I think we did get 0.866 on a few of those. And let's look at the tangent of 30 degrees. So choose tan 30 degrees, and it is in degrees. You don't need to put the symbol because it says degrees up here, and equals, it's 0.577, which I think we might have got on, we got 0.58 occasionally. It is approximate because, as you can see, there's no pattern with the decimal points, so it's 0.577. So we were pretty accurate with those, and the power is if you know what the angle is that you might be using in a triangle, and you measure, say, the height you've gone and the distance you might have travelled, it doesn't matter how far you go, you know that the ratio of the height to the distance you might have travelled here will be, the ratio will be 0.5. So that is very useful for engineering, for navigation on the Earth's surface, for astronomy, for travel, space travel. for building roofs, where you might need to have your eaves at a certain angle. It's very useful to know the sine and the cosine, and you can calculate missing lengths using that. So the same with the cosine here. It's going to be the 30 degrees, no matter, if you have 30 degrees, it doesn't matter how big your triangle, the adjacent divided by the hypotenuse will always be 0.866, that ratio. And for the tangent, the opposite over the adjacent. And tangent's very useful because we often have trouble calculating this angle, this distance here. So you can imagine if you were actually flying in, or you had projected a rocket taking a certain path, you might be able to calculate the height that rocket is and the distance that it may have travelled. You can calculate the angle of that trajectory, and you could even use Pythagoras to calculate the length of time, the length that it may have travelled, or the distance it's travelled. So this is illustrating that similar triangles here will have the same sine, cosine and tangent ratios of that angle. So thank you for listening. Bye for now.